Okay, so now we're going to look at potential energy due to elastic systems. And we are going to basically revisit some of the things that we talked about in Physics 1. And most of Physics 1, we spent time talking about potential energy in terms of gravity. Here we're going to look at potential energy in terms of a spring or anything that's elastic. So again, you think about potential energy. The potential energy is basically equal to the work that we put into a system if that work doesn't become kinetic energy. So when we compress a spring, we've got to put a force on it. That force will basically store energy in the form of elastic potential energy. When we release that spring, that energy can be realized as kinetic energy afterward. So again, just another way of storing mechanical energy. And if we look at the equation for it, it does take a little bit of calculus to understand this. We'll do this using equations. We'll also do it graphically. Here is our equation for work, okay? It's the integral of force over distance. Now, if that force were constant, this would be very easy. Work would just be force times distance. But the force, according to Hooke's law, increases as the displacement increases. At least the scalar value increases. So thinking about integration, one way to think about it is in terms of the visual aspect. And I'm going to draw a little graph right here. We have force on one axis, and we have displacement on another axis. So if we graph, according to Hooke's law, I'm not going to look at the direction so much. I'm going to look at the scalar value of the force. We know that it's going to be a straight line. Okay, so there's my force as a function of displacement. Now, obviously, we are going to compress a spring up to a certain point. So looking at, let's say, this point right here, this is the displacement that it's going to undergo. That means that if we want to take the integral, we're usually looking at the area underneath the graph. Okay, so we're looking at this right here. Now you recognize that shape as a triangle, right? And the area of a triangle is equal to 1/2 the base times the height. Okay, here the base is x, here the height is f. Okay, now in addition, the force is equal to, again, I'm going to ignore the negative sign, kx. So now it becomes 1/2 the base x times the height kx, or 1/2 kx squared. Okay. All right. So again, if you haven't had calculus, we've been talking a little bit about calculus in terms of derivatives are slopes, integrals are areas underneath the function. So right there, we sort of did a visual aspect. Now, if you have taken calculus, you know, again, that potential energy is going to be opposite to the work that is done. So we take the integral of this work, all right, we have kx. We're going to integrate it as a function of dx. Xi and xf are just the initial and final positions of the spring. So, we can pretty much say that xf minus xi is just going to be the total displacement. Okay, we'll be a little bit sloppy here. So I can take this k constant, I can stick it out front. See, it's out front right here. And I'm just going to do the integral of x. Now, for indefinite integrals, if I integrate x, it becomes 1/2 x squared. Okay, so again, I get the same result. I get the result that the potential energy is equal to 1/2 times k times x squared. Same exact thing I got by graphing it. So that's our expression for the potential energy of a spring. And again, you don't for this course necessarily know how to need to know how to come up with that, but it's useful to see where that comes from and why there's this 1/2 x squared dependence on this potential energy. Okay, let's see if we can come up with some different applications. Here we have what's sort of analogous to a spring gun. In physics 1, we use a spring gun to launch a projectile and basically determine how far the projectile would land based on angle and initial velocity. So look what's happening right here. In this particular system, we are putting work into, oops, wrong tool. We are putting work into the block by pushing it against the spring. We compress it. So here, the work done is going to be turned into potential energy. Here they're using PE instead of U. Sorry that we swap back and forth, but the potential energy is equal to 1/2 kx squared, where x represents the distance that we compress the spring, okay? Now, if I hold it in place, the block is at rest and the kinetic energy is going to be 0. When I release this, all this potential energy, as long as there's no non-conservative forces, obviously friction might play a role, all this kinetic energy becomes, potential energy becomes kinetic energy, which is 1/2 mv squared. So if we want to extend our work energy theorem, okay, our work energy theorem, work is equal to, another way of writing this is the following: the change in kinetic energy plus the change in potential energy, okay, due to gravity. We can add this extra term for the spring energy, okay? Anytime you have a conservative force, you can create a potential energy function for that, okay? Gravity, conservative force. Therefore, we have a potential energy for gravity. Spring force, it's conservative, okay? Again, according to Hooke's law, the force depends on position. So we've got something right there. You can also do it for other forces like electric fields, magnetic fields. So we're not really doing anything very different. We're just considering now potential energy due to a spring. So once again, the non-conservative work done, this is energy coming in from the outside or being dumped into the outside. Okay, it could be from that hand pushing on the block and spring. It could be from friction, which is turning the mechanical energy into heat. Okay, this is the energy that's coming in or out of the system. Is going to be equal to the change in kinetic energy plus the change in potential energy, both gravitational and spring energy. All right, here's just another way of writing it. Instead of writing in terms of delta, which is final minus initial, we moved all the final quantities to the right. We've moved all the initial quantities to the left. Get basically the same result. In this particular case, we say that the non-conservative work is 0. Okay, if all mechanical energy is conserved, it makes sense that all the energy before an interaction is equal to all the energy after an interaction. Okay, once again, looking at it, a similar system, we have a block coming in. Instead of doing work on the block, pushing it, the block comes in with some kinetic energy, okay? That kinetic energy compresses the spring, we should say the kinetic energy is converted into potential energy as the spring is compressed. And at the point where the spring is compressed to its maximum amount, all the kinetic energy has gone away. Now we're at velocity 0, and that's turned into potential energy, okay? If there's no friction here, there's no non-conservative work, the kinetic energy is converted into potential energy, And then that potential energy can be converted back into kinetic energy as a spring pushes on the block. It's an idealized system because obviously there's always going to be a little bit of friction there. Again, we're just transforming energy from one type to another. Kinetic to kinetic plus potential to all potential, and then back to all kinetic. Okay. Back to the simple harmonic oscillator. Simple harmonic oscillator is, once again, just a mass on a spring. There's our spring, some spring constant K. There's our mass. Okay. Now, at equilibrium, if this block is at rest, this mass is at rest, the total energy of the system is basically going to be zero. All right? There's no kinetic energy. There's no potential energy. All right? Block's not going to move. However, if I pull on this block, okay, I displace it some distance x, okay? Actually, I'm going to say x is equal to a. And displace it some distance a, because that's going to be the amplitude of the oscillation. Now I've done work on the system. Now we have energy, all right? When it's at this new location down here, all the energy is in the form of potential energy. If I release it, the force from the spring is going to pull it upward. It's going to begin to move. It's going to begin to accelerate. And that potential energy then becomes kinetic energy. Now, we know that a simple harmonic oscillator moves something like this, follows sort of a cosine or a sine. Up and down, okay? We also know, I drew the equilibrium position the best I can, that when it's at equilibrium, the potential energy is zero, okay? When it is at its maximum amplitude, this is A, the potential energy is maximum and the kinetic energy is zero. So I want to come up with an equation that allows me to know how fast this harmonic oscillator is going at any one point. Okay. I can use calculus to do this, to do it as a function of time. But let's get away from that. How fast is it going at any position? Well, think about this. When it's up at this point, all the energy is potential. It's 1/2 k x squared. X is equal to a. So we say that's a squared. Okay? And in fact, at any point, the potential energy is going to be 1/2 kx squared. When the block goes through equilibrium, we know that the velocity is the fastest. There, the kinetic energy is going to be equal to 1/2 m e squared. So the total energy of the system is going to be 1/2 k a squared. Okay? We can look at the kinetic energy at any one point by solving for V, okay? And basically, if we set that equal to 1/2 k a squared, we can get rid of the 1/2 on both sides. Okay, get rid of this side and this side. We solve for V, okay? V squared is equal to k over m a squared, okay? This is when it's passing through equilibrium. All right. And then V is equal to the square root of K over M, A squared. All right. It's not so difficult to talk about this and say, all right, if we subtract off the potential energy from what the kinetic energy is, we can rewrite this. I'm not going to go through the whole derivation and allow it to go up and down, by the way. Change this to K over M equals A squared minus X squared. And that becomes my expression for velocity at any point for this simple harmonic oscillator. And again, it's just conservation of energy. We consider that there's no energy loss due to work. So in this particular case, the velocity depends on the kinetic energy, and the kinetic energy is really the total energy minus the potential energy. Okay. All right. Here's a sort of simple problem showing how energy is transferred from one type to another. We have a car at the top of the hill. It has all of its energy in terms of potential energy due to gravity. It's going to accelerate downward. That energy is going to be turned into kinetic energy, and then it's going to collide with this guardrail hooked to a spring, turn this into potential energy due to a spring. Now, nowhere do they ask for velocity, so I don't really have to worry about ever converting the potential energy due to gravity to kinetic energy. I can go directly from gravitational potential energy to spring energy. Okay? So that's what I'm going to do right here. I'm going to set my gravitational energy equal to the spring energy. Gravitational energy, potential energy, is equal to mgh. The spring energy is equal to 1/2 kx squared. Okay? So the initial energy is all gravitational potential energy. The final energy is all spring potential energy. So I set them equal to one another. X represents the maximum compression. H represents the maximum height. Okay? So I'm solving for X right here. I solve for X right here. I'll divide both sides by K. I'll multiply both sides by 2. Okay? Then I take the square root on both sides, and I get my final expression right here. Okay? Very simple conservation of energy. All right. Again, we're doing these examples without friction. Friction is going to do work on this. This just allows us to quickly go from potential energy to kinetic energy and back to potential energy without having to worry about energy loss due to the system. So a 1.6 kilogram block on a horizontal surface is attached to a spring with a spring constant of 1,000 newtons per meter. So there's my K. The spring is compressed to a distance of 2 centimeters, that's 0.02 meters, and the block is released. So the first thing I need to do is, okay, spring is compressed. I know what the spring constant is, it's 1,000. I know how far it's compressed, 0.02 meters. What is the velocity as the block passes through equilibrium as it's released? Okay, so in this case, all of this potential energy is going to be turned into kinetic energy. So I'm going to set potential energy equal to kinetic energy, potential energy equal to kinetic energy. And just like I did before, I'm asking for, what is the speed? I'm going to solve for V. Divide both sides. Well, you can get rid of the 1/2, multiply both sides by 2. Divide both sides by m, then take the square root of both sides. And I get the square root of k over m. X is squared, so when we take the square root, we get back x. So 1,000 divided by the mass, 1.6 kilograms, square root, times 0.002. Remember, we're all in SI units, so I gotta convert centimeters into meters, okay? And that gives me 1/2 meter per second, okay? Now, again, you could have used the previous equation. Remember the previous equation said V equals plus or minus the square root of K over M X squared minus A squared. Sorry, reverse that. We can't have a negative here because X can never be greater than A. I wrote that backwards. Again, A squared minus X squared. And you can use that, you get the same exact result. All right. Okay. Yeah, in this case, what is X in this equation is actually A here. You get the same exact result. Okay, let's go on to the next. Calculate the speed of the block as it passes through the equilibrium position if a constant force of friction of 4 newtons acts against the motion of the block. Here, things get a little bit more difficult, okay? We have a non-conservative force here. We have friction, and that friction is going to act against the motion, negative F times the distance, okay? Friction is constant, right? When we calculate the work, we can just do force times distance because the force is constant. And now we write work, non-conservative, is equal to the change in kinetic energy plus the change in potential energy, okay? So the block's going to get going faster, so the change in kinetic energy is positive, whereas it's going to lose potential energy as the spring expands. All right. So now we solve for V again, okay? Multiply both sides by 2, divide both sides by M. Here's our expression. A little bit longer, and you notice that instead of 0.5 meter per second, now we're down to 0.39 meters per second. Okay? More realistic, right? Now we're actually including friction in here. And it's not surprising that we go from a higher velocity to a lower velocity because we lose mechanical energy. Okay, this is an interesting representation of pretty much what's going on with a harmonic oscillator. If no work is being done, where work is being added or lost, we basically say that the total energy of the system, let's call that E, is going to be constant. That energy is going to be equal to either 1/2 K times the amplitude squared, or equal to 1/2 the mass times the velocity at equilibrium squared. They're both the same energy. All right. So again, that velocity, that energy is constant. But we can see in here how the energy is traded back and forth, right? When the spring is either most compressed or most stretched, the position is equal to A, so we have the maximum amount of potential energy. As it passes through equilibrium, however, that potential energy drops to 0, okay? When X equals 0, 1/2 kx squared is equal to 0, so there's no potential energy left. Then it begins to either compress or expand again. Now it stops. All the energy is potential energy, all the energy is kinetic energy. Back and forth, okay? The kinetic energy is gaining whatever the potential energy loses. So at maximum amplitude, it's not moving, it's turning around. As it approaches equilibrium, the kinetic energy is maximum. Here's our equilibrium point. Here's our equilibrium point. Here's our equilibrium point. Okay. Our kinetic energy is maximum because it's traveling the fastest. All right. And we can see how that traces out. And again, as long as we don't lose any energy, this will go on repeatedly. All right. So this is graphing energy as a function of time. All right. If we think about the position as a function of time, we know what's my potential energy. My potential energy is in red. Okay, I'll keep that right there. We know the potential energy goes by 1/2 kx squared. We know that x goes by a cosine omega t. So when we're graphing this, this red function actually is, x squared is a squared cosine squared omega squared. So that's a cosine squared function that we're seeing right there. Okay? You can do your trig identities, actually see that you can break that down into a trig function. In any case, now if we look at the graph of energy, graph not versus time, but rather position, we see this, okay? Notice, let me do potential energy first. Notice potential energy has this x squared dependence on it, okay? This is a graph of a parabola, right? You clearly see that parabola right here. At the vertex of the parabola, down here at equilibrium, there's no potential energy, okay? At the maximum amplitude, we have x squared is its largest value, so u is also its largest value. In this relationship, K is equal to the total energy minus U, okay? Here's the total energy right here again. So I didn't get that completely right. I got a little distance there. The potential of the kinetic energy looks just like the mirror image of the potential energy. All right. So it's just another way. This is an energy diagram. It's just another way of viewing what's going on. And if there's no non-conservative work that's being done here, it's just energy sloshing back and forth from one type to another type.